So here we are in Chapter 20, Electrochemistry, after we've talked a bunch about balancing redox reactions, and we're back to asking the question, where are we? So far, what we've done is we've decided that electrochemical reactions occur from oxidation and reduction reactions. In oxidation and reduction reactions, we have a transfer of electrons, and we've hinted that this transfer of electrons is the thing that creates electricity, and we'll see that more now. These reactions occur spontaneously, and if you remember from back in Chapter 19, that means they occur without outside intervention. We can represent these oxidation-reduction reactions with what are called half reactions. Half of it as oxidation, half of it as reduction, and we'll continue to look at that. And we can balance these oxidation and reduction reactions to show the electron transfer. To show the electron transfer, oxidation is the loss, and then the reduction is the gain. So where are we going? So far we've done these things. Where are we going with this? In this video cast, we're going to use these electrons. We're going to use these electrons to create electricity, and we're going to talk about how that, we're going to describe that flow of electrons. We're going to create this electron flow, and we're going to call this electron flow thing a battery. And we're going to give it some fancy names. We're going to call this battery thing a voltaic or a galvanic cell. Those fancy words are going to be used. So I encourage you to have your book out. You can follow along. We're going to start on page 855 of Brown, LeMay, Burston, and then also have some paper out to follow along. And I encourage you to have a pen or a pencil out as well. And then you can follow along with these. And we'll do a tiny bit of math, but not a lot during this as well. We're going to describe these redox reactions that actually have electrons that transfer. All right? I'm going to start right here on page 855 where it says Voltaic Cells. Voltaic Cells. The energy released in a spontaneous redox reaction can be used to perform electrical work. This task is accomplished through what's called a voltaic or a galvanic cell, a device in which the transfer of electrons takes place through an external pathway rather than directly between reactants. One such spontaneous reaction occurs when a strip of zinc is placed in contact with a solution containing copper. As the reaction proceeds, the blue color of the copper ion fades, and the copper metal deposits on the zinc. At the same time, the zinc begins to dissolve. This transformation is shown in figure 20.3 and are summarized by this equation. You can see right here that zinc becomes zinc plus 2, aqueous, and copper aqueous becomes copper solid. And I'm going to focus mostly on this figure right now as I talk about it. And if you want to have your own figure out in front of you, you're more than welcome to. Otherwise, I'm just going to talk through this one on the molecular scale as well. Notice how we've got this strip of solid zinc right here. And it's inside this blue-colored solution. That's copper nitrate probably. And then after a while, you can see that the zinc atoms right here, zinc atoms become zinc positive 2 ions. And that the copper ions, these blue ones right here, copper plus 2s, gain some electrons from the zinc and start to become copper atoms, and they tried to make it kind of copperish colored right here. You can see that it's dark colored in here as well. This is a spontaneous flow of electrons from zinc to copper. We want to be able to harness this exchange of electrons from zinc being oxidized and copper being reduced and make those electrons do some type of work. These electrons do some type of work. Well, the way to make that happen is to create what's called an external pathway so the zinc and the copper solution aren't touching each other right away. And there's two figures right here on the next page that actually do a really nice job of that. And I'm going to zoom in on this one, even though it's not the exact picture. And I'm going to show you and kind of describe how this harnessing of the electrons actually works. This is a picture of what's called a Voltaic cell. A Voltaic cell. I'll zoom out just a little bit so I can read the words. It's a reaction between zinc and copper that was given in the equation down below here. Well, actually on the page before. And although the setup isn't exactly the same as the zinc being stuck into the copper solution, the reaction is the same. The significant difference between the two setups is that the zinc metal and the copper plus 2 ions are in here, and the zinc metal is over here, are not in direct contact. Instead, the zinc metal is placed in contact with zinc plus 2 ion solution. This is zinc nitrate solution, and this is a zinc solid chunk. The copper metal right here is placed in contact with copper nitrate solution in another compartment. Notice these two beakers right here are simply separated from each other. They're called compartments. Consequently, the reduction of copper plus 2 can occur only by a flow of electrons through an external circuit, namely a wire right here that connects the zinc and the copper strips. In other words, by physically separating the reduction half of a redox reaction from the oxidation half of the redox reaction, we create a flow of electrons through an external circuit. The two solid metals that are connected by the external circuit are called the electrodes. This is one electrode right here. This is another electrode right here. By definition, the electrode at which oxidation occurs is called the anode. And remember, zinc goes to zinc plus 2. If we'd separate the half reactions, you can see that zinc is oxidized. And remember, oxidation begins with a vowel, and anode begins with a vowel. If you remember anox, that's how you can remember the anode is where oxidation takes place. Anox. By definition, the electrode at which reduction occurs is called the cathode. The cathode right here is where copper plus 2 gains electrons and becomes Cu solid. And you can remember red cat because reduction occurs at the cathode. And reduction is the gain of electrons right here. The electrodes can be made of materials that participate in the reaction, as in the present example. Over the course of the reaction, the zinc electrode will gradually disappear and the copper electrode will gain mass because the copper plus 2 ions will become copper solid, and this electrode will grow in size, grow and become more solid. There will be more solid on them. The zinc electrode will eventually look like it's been eaten away because the zinc will all become zinc plus 2 ions. More typically, the electrodes are made of a conducting material such as platinum or graphite that doesn't gain or lose mass during the reaction but serves as a surface from which electrons are transferred. We'll look at one of those electrochemical cells in a little while. Back to this one. Each of the two compartments of a Voltaic cell are called a half cell. This is a half cell right here, and this is the other half cell. Just like we have half reactions, we have half cells. In our present example, zinc is oxidized and copper is reduced. And you can see the equations right here where zinc is oxidized and copper is reduced right here. Electrons become available as zinc metal is oxidized at the anode. They flow through the external circuit right here. You can see the electrons flow through here to the cathode over here. Notice the cathode has a positive symbol because the electrons, which are negative, are attracted to the positive sign over here, where they're consumed by the copper plus 2 ions. See the copper plus 2 ions? They glom onto these electrons that flow through this solid copper right here, and then they precipitate or become a solid around this copper metal right here. Because zinc is oxidized in the cell, the zinc electrode loses mass, and the concentration of zinc plus 2 ion solution increases as the cell operates. Similarly, the copper electrode gains mass, and the copper plus 2 solution becomes less concentrated as the Cu plus ions are reduced to become Cu solid. So there's less Cu plus 2 ions and more Cu solid. For a voltaic cell to work, the solutions in the two half cells must remain electrically neutral. As zinc is oxidized, zinc becomes zinc plus 2. In the anode compartment, zinc plus 2 ions enter the solution. Thus, there must be some means for positive ions to migrate out of the anode compartment, that's right here, out of here, or for negative ions to migrate in to keep the solution electrically neutral. Similarly, the reduction of copper plus 2 ions, see these copper plus 2 ions right here? They become copper plus. And since you're removing positive charges from the solution, it leaves an excess negative charge in that half cell. Thus, positive ions must migrate into the compartment or negative ions must migrate out. In fact, no measurable electron flow will occur between electrodes unless a means is provided for ions to migrate through the solution from one electrode compartment to the other, thereby completing the circuit. In this figure right here, you'll see that there is this bridge right here, okay? This allows a migration of ions that maintains the electrical neutrality of the solution. This is called a salt bridge. A salt bridge. And a salt bridge provides positive ions, in this case Na pluses, and negative ions, NO3 minuses, that, well, they're called an electrolyte solution, whose ions will not react with the ions in the cell or with the electrode materials. The electrolyte is often incorporated into a paste or a gel so that the electrolyte solution does not pour out when a tube like this U-tube is inverted. As oxidation and reduction proceeds at the electrodes, ions from the salt bridge migrate to neutralize the charge in the cell compartments. Whatever means is used to allow ions to migrate between half cells, anions always migrate towards the anode, cations always migrate towards the cathode. Anions towards the anode, so that's the NO3 minuses towards the anode right here, because you need some negative ions to come and balance these positive ions that have formed, and positive ions, cations right here, towards the cathode to neutralize the lost copper ions right here, because the copper plus 2 ions become copper solid. This figure summarizes that relationship with the anode and the cathode. Notice in particular that in any voltaic cell, the electrons flow from the anode through the external circuit to the cathode right here. Because an anode in a voltaic cell is labeled with a negative sign and the cathode with a positive sign, we can envision the electrons as being attracted to the positive cathode from the negative anode through the external circuit. So we can take a look at another example of this picture on the next page right here. And you can see in this picture right here, it's the same kind of cell with an anode and a cathode, but they don't have a salt bridge this time. They have a porous barrier where the anodes and cathodes can shift between. The engineering of this is actually really interesting because this is how batteries that you use in your cell phone, in your flashlight, in anything that uses batteries are constructed. And you don't see big tubs of solution like this in batteries. You usually see that this stuff right here is in some form of a paste, or if you've ever taken a AA battery apart, you'll see that it's kind of damp, but it's kind of some gooey stuff that allows the flow of anions and cations and therefore electrons. On the next page, they actually go through a molecular view of the electrode process. And I just want to point out on this picture right here, what happens in this cell that we were talking about, and how at the zinc half cell, where the solid zinc strip is, it loses electrons, therefore it's oxidized. And these electrons are gained by the copper plus 2 ions. And then over here in this side, you can see that it forms some copper atoms that actually form. Now, this is separated, of course, in a galvanic cell. So then you can actually harness that electron flow to do some type of work. And as you saw back in this picture, they actually put what's called a voltmeter there. You could have something that actually uses this electricity, like a flashlight bulb, which runs from a battery, or a little motor, like a fan or something like that. And those electrons that flow through there would actually drive and cause that to happen. So I'd encourage you to take a look at a little bit more of this molecular view of the electrode process on page. This is on page 859 of the 10th edition. Of course, you might have a different edition as well. And you can see another setup of this thing called a galvanic or voltaic cell right down here, and a little more of the atomic level depiction. In our next video casts, we'll actually look at, now that we know this electron transfer can occur, how can the transfer exchange be harnessed? And we looked on page 885 of your text and following, but we'll actually look at numerically how can we calculate how many electrons flow, and then from that what kind of charge it will cause, and then from that kind of charge what kind of energy is available to do some work. And just looking ahead in your textbook, in section 20.4, we can actually talk about this force that drives these electrons, or this force created by these driving electrons. And they give it a fancy, fancy name. They call it the EMF, or the Electro-Motive Force. That's what EMF stands for. That is caused by this spontaneous flow of electrons. This difference in pushing of electrons is actually measured in a unit that maybe you've heard of before. It's actually called something called the volt. And this volt is defined as the amount of energy per unit of charge that we have, a joule per coulomb. And in our next video cast, we'll look a little bit closer at how the volt was derived and what we can actually think of as amount of electromotive force for these cool electrochemical reactions. So hopefully you got a little bit of a background, and you can use this information going on to the next video cast to be able to mathematically describe electromotive force.